Hello, so in today's video, we're going to learn how to combine YOLO-NAS and OC-SORT together to do some visual object tracking. So YOLO-NAS is a recently released model from DESI AI under this library called SuperGradients, and it's a new state-of-the-art object detector that outperforms YOLO v6 and YOLO v8 by a pretty good margin in terms of speed and accuracy. So sort of the secret sauce around YOLO-NAS is its neural architecture search. So what that is, it's an intelligent way to select a model architecture for optimal performance. And you can see right here in these small, medium, and large models, we have our, these are kind of our baseline performances for YOLO-NAS, but when we quantize them, so in this case, we have the regular models. They're represented in 16-bit floating points, but we could actually reduce their weight representation to 8-bit integers with a small performance cost to pay in terms of accuracy, but a large gain in terms of speed. So for this large model right here, we go from 7.8 milliseconds to 4.7 milliseconds, and we still maintain a similar accuracy. And that's a pretty big deal. And that makes this pretty useful and potentially useful for real-time applications. So the other side of what we're integrating today is called OC-SORT, or object-centric sort, or observation-centric sort. So I would say currently SORT is probably the most popular object tracking algorithm. It's pretty easy. You just go fork the code from GitHub or copy the script from GitHub and add it to your application or whatever you're doing. OC-SORT is similar, but it's actually a little bit better, and it improves off of SORT in a couple of ways. So it has something called observation-centric re-update, which reduces common filter error after a track is unobserved for several frames. So in the paper, they show that the error actually is exponentially increasing every time there's an observation is not made, and even when an observation is made again, even when something is reassociated, it could still lose it again, as in this case. So OC-SORT has a method to actually reacquire a track and to keep tracking it, which is pretty useful. So there's also observation-centric momentum. So this adds an expected motion direction into the cost association matrix, along with the IOU, or intersection over union cost. So it combines those. And then another thing is observation-centric recovery. So this is basically a secondary association heuristic to help prevent lost tracks. If you want more details, there's an article or the paper. I'll link both of those below, and you could go through those for some more information. So let's get started on the code. So we're going to have several rounds of imports. So this fast core, I had some issues. I basically went to Stack Overflow and said to mention install fastcore, and it seemed to fix some of the issues I was having. I think it was an issue with like PyTube or something. But so I did that, and this right here is for super gradients. So in order to use YOLO-NAS, we're going to need to install all this. Make sure you're not using PyTorch 2. As of currently, super gradients is not compatible with PyTorch 2, so we got to use PyTorch 1. So I've already ran these. These actually take a while, and then I have some basic stuff to handle our video, FilterPy for our tracking algorithm. I've actually already ran this, did not mean to do that. And then once we do all these installs, you'll need to restart the environment in order to use the new stuff. So next, we're going to get the OC-SORT code. We only need 3 scripts. So on the OC-SORT GitHub is the main page. We go to trackers, OC-SORT tracker, and we're going to need to get all 3 of these scripts. So here's the main script, is OC-SORT Pi, and basically it's very similar to the regular sort script. We have our OC-SORT object, and then we initialize it just like we would with sort. So to copy this, we go to the raw, and we just copy the raw URL, and then we go here, use the wget command. In this case, I created a new directory, use the wget command, and download it to our new directory. So Jupyter's a little bit laggy right now, but it's in this new directory called OC-SORT. I've already ran this. So now we have our library imports, and now we're going to download a video from YouTube. You can use any video from YouTube to do the tracking on. In this case, since we're using YOLO-NAS, we're going to use a NASCAR video, and I'll show you what the results look like towards the end. So here's just our save path for saving the video, and we're going to want to save it with audio. So right here, we're going to import our YOLO-NAS model. We're going to use the small model, hence the S. And for what we're going to do today, we're going to need to set this in eval. Now this is pretty trivial, but the API for super gradients is pretty high level, and you don't really need to do too much. But we're going to actually bypass the API a little bit and get a bit of a speed up, and I'll show you how to do that in just a second. So right now we're just going to get a test frame from the video we downloaded from YouTube, and we're going to get a baseline test with the regular API. So with the regular API, we take our RGB image. This is a NumPy array, and so I convert it to NumPy right here, and right here an image in. I just make a copy so I don't do anything weird to it. So right here is what the API does. It takes the model, and we call this model.predict function. Now this is not the forward function, it's a special function from super gradients that will give us a set of predictions, and I'll show you what they look like down below. Jupyter's a little bit laggy, so I won't go to it yet. So right now here's our predictions. In order to get our input to OC-SORT, so OC-SORT's update function takes this variable called output results as its main argument, and this is basically an n×5 array of bounding box coordinates and confidence score. So to get that here, we get our predictions and bounding boxes and predictions.confidence, combine those. So what is this right here? This output right here is actually a generator. So we call the list on it and get the first element, since we're only doing one image at a time. And then we get our detection array that we can actually pass to our tracker. And this thing right here is what actually gives us a lot of overhead. And we're going to attempt to use the API or exploit the API to bypass this. So I did this test with 100, ran inference on the same image 100 times, and we got an average of 15.6 hertz, and that's not too bad. I would think, given this, what I've seen here, I would imagine it would be a little bit better, given that it says we should be at 3, but this GPU is probably not as good as the one that they're using to get these results right here. They're using it in NVIDIA T4. Let's see here. Oh, I'm on a T4, but okay. Well, in this case, we're only getting 0.06 seconds, so 15 hertz. So in order to leverage the API, it's useful to see what this model predict function is doing, and we could actually find out where this is taking place in the code by leveraging the inspect library. So we could just do this call right here, inspect get file model predict, and we just call os_abs path, and it gives us the exact location of where this thing is. So right here we've downloaded the library with our commands above into the environment, and in super gradient, since it's under training models, detection models, customizable detector. So I'm not going to go through the code, or not going to go through the super gradients code. I've gone through it earlier, but essentially it makes, in order to do it, actually, I will go through it real quick. So I'm going to go to super gradients, just real quick. I already forgot. So training models, detection models, customizable detector. Okay, so customizable detector, we have this customizable detector object, and we have the predict. So this is what we are actually running when we call the predict on our model, and it basically returns the pipeline with an image. So, and we go to get pipeline, and it's actually this detection pipeline. So we're going to make our own detection pipeline in our notebook, and that is what we're doing right here. So it takes a model, an image processor. We could do this with everything that we have for our current model. The important thing to know about the image pipeline for this case right here is that we need to set the IOU and confidence thresholds right here, and we're not going to do this in the prediction function. So in this case right here, normally when we call predict, we set prediction and confidence. If we don't, it just gives us a default value, but we need to do that right here in this pipeline we define. So when this thing stops lagging, I'll show you the function that we use to detect the actual object. So right here, I call this function get prediction. So this is also sort of paraphrased from the supergradients code. So we can easily pre-process the image with a pipeline attribute to pre-process the image. We can do our predictions right here. Some old code. So we can get a torch tensor, put it into the model, and then we could get our prediction right here. So this helps us decode our model output, and then we do some final post-processing and return, and this gives us our prediction right here. So I've ran this a bunch of times to get our XY, XYC detections for our tracker, and we actually get a pretty good speed up. We go from 15 hertz to 20 hertz just by bypassing the bulk of the API. Now we could still write some more custom stuff to get rid of all this overhead right here. I mean, this is still doing quite a bit of stuff, but it might not be entirely necessary. So we're just gonna go with this right here. And just for brevity, to determine that this is the actual output. So right here I have the prediction that came from the function, and below I have the image predictions. So just a quick manual check, we'll do the first one. We do 6.54, 6.54, and then the last one, 4.68, and 4.68. And you can roughly see that the labels on each side are roughly the same. So I'm pretty confident that these are the same, and the output results also look pretty good. So right here, we are going to actually get the video frames per second for later and save the audio to add that back in later. So that's just nice to have to create the output video. So this is how we instantiate the OC-SORT tracker object. Very similar. We just have this one detection threshold parameter, and now we have our tracker object. This right here is a special function to get uniquely colored bounding boxes for each track, and we get these colors in HSV space and convert back to RGB. The use of this function is it gives us very different colors for closely spaced numbers. So if we have like 10 tracks 1 through 10, and we run this function right here, we're going to get very different colors so we can distinguish our different tracks. So right here, we're actually going to resize the image to half in order to do inference. I've experimented resizing to the original size. It seems like the detections are pretty bad when I do this, so I decided not to do it. So OC-SORT is kind of nice in the sense that it'll automatically rescale the images if we perform inference on a smaller image. So what this image info is our original image, and this is our image size is what we inferenced on. So that's kind of nice. Instead of scaling them ourselves, we don't really have to because it takes care of it for us. So right here, I've tuned the detector main threshold mainly since the video we're going to watch is actually very hard to make tracks on. It's got a lot of fast-moving cars, a lot of blurriness from those fast-moving objects, and the camera pans a lot, which messes everything up. So the default maximum age is 30, and I reduced it to 10, and I decreased the minimum hits to 2. Since due to the fast-moving objects, we'll probably lose track. I want to reestablish track faster. So right here's some stuff just to count the frames per second. So we're going to iterate through this video, get our frames, get our inference, get our detections, feed these into the tracker, and then for all our tracks, we're going to draw them on the frame. We're going to update our FPS right here, and then we're going to actually add that to our frame so we can know I'm going to add these to a list to make a video later. And here's an example of what one of the frames looks like. So you can see there's kind of some jumbledness up here. But for the most part, these people that aren't moving around, the tracks look pretty well behaved. So we're going to save this to a video, add back the audio in this step, and I also have the results of what this looks like. So let's see that. Basically, as soon as the camera pans, it messes everything up. But you could also see right here is the track number. Here's the number of hits that the track has received. You can kind of see those continuously counting up. And you can see we don't really get a lot of tracks, and if we do get them, the tracks on the other side of the track, they kind of go away quickly. These cars are pretty blurry, and we're also got to remember we're only doing inference on half the image size. So you can see that even these cars are, even with a little bit of camera motion, we get some of the tracks right here. But there's still some issues that happen with drop tracks, and then of course everything goes crazy when the camera moves too fast. So that's it. I think the tracker tuning could be a little bit better, but I think you should get the idea of how to incorporate these two things together, YOLO-NAS and OC-SORT. So I hope you enjoyed it, hope you learned a little bit, and I'll see you in the next one.